All right, we've done a lot of hard work, a lot of calculations, and ultimately what those calculations have gotten us down to is the two key pieces of information that we need in order to draw that magical regression line. That is the slope of our line, or the beta 1 value, and the y-intercept of our line, or the beta 0 value. These are the two pieces that we need to draw that line and to then make predictions. So let's take a look. We're actually going to chart these out into a line and see how close we came. What I'll do is we will take each one of those, insert it into the regression equation. So remember, when we're trying to predict final score or final grade based on your exam 1 grade, this is the formula that we're going to use. So let's see how it actually compares when we have a statistics program like Microsoft Excel calculate the very same thing. So this was ours, this is our estimate, and here's where Excel calculated it. As you can see, not too bad. So we had 0.4, they had 0.4028, we had 69.51, they had 69.517. Remember, we rounded all of our variables to 2 decimals, so it's no surprise we're a little bit off, but overall not bad. And remember, what this equation is this is the equation for that line in other words, for the series of predictions that we can make of a final grade based on an exam 1 score. So let's see what that would actually look like. In other words, how could we actually use this regression equation? So if we insert a value for x, then we should get y. So let's imagine that you'd just taken the first exam and you'd scored, for instance, a 50 on it. What you do is you insert that 50 right where the x goes. So 0.40 or 0.402 times 50 plus 69.51, and what that'll give you is 89.61. In other words, if you scored a 50 at time 1, our best guess is that you would score about an 89.61 on your final grade. This is what the line of best fit does. But it raises the question, what exactly do we mean by the line of best fit? When we say that the regression line is the line of best fit, what we mean is that of all the possible lines we could draw, it comes the closest along the y-axis to touching every point. In other words, if we're trying to use x, here exam 1, to estimate y, final grade, it gives us the smallest possible error in estimating our final grade knowing x. So what do we mean the smallest possible error? What does that actually look like? Well, I just want to show you visually what those errors look like. So if this is the best fitting line, what we can see is that it's still off. It has to be. These points, all of these points all over here, do not fall on a perfect line. So what these arrows represent is how much that regression line underestimates some points. In other words, for all of these points, when we try to predict their final score, we're going to miss it. We're going to underestimate it. They deviate above our regression line. For all of these points, we're overestimating their scores. For instance, this person scored a 50. We thought they'd score about an 89, but instead it looks like they score about an 84.5. We have overestimated those scores. We've underestimated these scores. What we can think of is we can think of these as deviations. So if we take all of these deviations, both the underestimates and the overestimates, and if we add them all up, so in other words, you can picture or imagine stacking all of these arrows end to end to end. One of the ways you can think about this is how much error is left in our regression line. In other words, this is the amount of variance that remains around the regression line. But is this good or is this bad? I mean, is this a lot of error or is this not too bad? Another way of saying that is, what is this line of best fit better than? If it's the best fit, what is it better than? Well, the thing that typically, remember, if we know nothing about the relationship between two values, we can still make a guess about their values. So like we talked about before, even if I didn't know a student's score in the exam, I could still make a guess as to their final grade in the class. If you didn't know anything about the student, but you had all of the class scores and you knew that that student was in the class, how would you best guess their score? Well, that's what we've talked about before. In statistics, this best guess, we typically rely upon the average or the mean. It's the best fit between all of the scores, knowing nothing else about them. So in other words, by using the average, you're most likely to make a smaller error. So let's see what would happen if we simply use the average right here to guess students' final grades. How off are we? We can see for some people here, we're underestimating their scores. For others, we're overestimating. But is this better or worse than we did with our other line? Well, we can do the same thing again where we take all those deviation scores and we stack them end to end to end. So now let's compare these deviations, the deviations from the mean line to the mean deviations from the regression line. As we can see, while it's not a huge difference, there are nevertheless slightly more errors in the mean line in using the average to estimate than there are in using the regression line. Now, this may not seem like very much difference, but it can significantly reduce our error over the long run. So the second question, and it goes along with this first one, is does our regression line actually predict any better than chance? Well, it looks like it, but by how much does it reduce the amount of error between each point and the mean y value? In other words, going back to our previous slide, how different is this? And is this difference significant, or is it significantly different from chance alone? So in order to figure out, we'll have to perform two more, you guess, calculations. So first, what we have to calculate is the variance around the mean. In other words, how much variability is there in final grade? Luckily, we've already done that. We can celebrate. That's what our sum of squares y is, and then when we take the average sum of squares, that's our variance of y. This is the total amount of error that we get when we use only the mean value to predict our outcome. This is also sometimes called the sum of squares total, and we'll come back to that when we talk about ANOVAs. So remember, the sum of squares over here, sum of squares y, is all of those squared deviations around the mean of y. In other words, this is how much people are varying in terms of their final grade in the class. The way to picture that is here is y, here are the deviations from y, and so when we square them, we simply make them all positive and we add them up like we just saw before. The next thing we have to do is we have to calculate the error in our predictions. So if this is all the errors just around the mean, or how much variability there is in general, how much error do we have in our predictions? So from our data, what we're going to do is take each of those x values into the equation, and we get at our predicted y. So we'll plug in each one of those. So for instance, if we had x is 50, what we do is enter that into the regression equation, do 0.402 times 50 plus 69.51, and what we're going to get is our predicted value is 89.61. And then from our data, what we do is we take a look and see what they actually scored on y. This is what we predicted they would score using our regression line, but what did they actually score? In this case, this student's final score was 90. So what we do is we find out what is the deviation between their actual score and what their actual score is right here and what they predicted it would be. And what we find is that's actually a very small deviation. And then to make it positive so we can add it up, we just square this value. 0.185. And in the end, we do that for every single person. We sum up all of those squared values. This is also the error that we get when using our regression equation to predict y values, our sum of squares error. And the sum of squares error we're going to find is actually a very common term in statistics. But we've already seen what this looks like. The sum of squared, each one of these little deviations here, the difference between an individual score, like this one, and a predicted, the difference between a predicted score right here and their actual score on the y-axis, this is our deviation, this is our error. And what we're going to do is calculate that error for all of them. We've already seen that before. And ultimately, when we square it and add it all up, we can stick those end to end to end, and that's where we end up getting the square of our error. So I've done that for you here. What we've done for each one of these is we've taken, for instance, the actual y. We've calculated out what their predicted value of y would be. When we do the first one minus the second one, we're going to get the error or the deviation in our prediction. And when we square that and then add those all up, what we end up getting is a sum of squares for error. In other words, how off was our calculation? So we have a sum of squares for y, just in general, how much do scores differ from the mean? And then we have our sum of squares error. If these two things are identical, we've done absolutely nothing by drawing our regression line. The smaller this one is over here, the smaller our error squared is, the better we've done. So finally, we can calculate out what proportion of the total variance is reduced by the regression line. So in other words, we're just going to take the sum of squares total, which is how much people differ in general on their final exam grade. We're going to subtract out the sum of squares error. This is how much people differed from our regression line. And then we're going to divide that by the sum of squares total again, by that variability. In other words, this is asking, this top part right here is how much better did we do than chance alone? And we're going to put that into a reasonable number by dividing it again by the sum of squares total. And our result here is known as r squared. For this one, our r squared equals 0.153. And if we take the square root of this, we get r, or the correlation coefficient. So here we get r equals 0.392. We've seen what those r's looked like in weeks past, but I just wanted to show you how you end up deriving it in the first place. The one last thing to say is r squared over here is also known as the coefficient of determination. Another way of thinking of it is the percentage of variance in y, and here y, remember, is the amount that we know, the percentage of the variance in final grades accounted for by x. In other words, if we only know x, how much can we know about someone's final grade? And it turns out of all the 100%, if this was 1.0, if r squared was 1.0, we would perfectly predict their final grade based on their first score. In other words, there'd be no variability in their final grade that wasn't due to that exam. If it's 0, our first exam grade tells us nothing. And here, r squared tells us we can account for 15.3% of the variability in their final grade. In other words, of the whole pie of variance, of all the reasons why someone's final grade differs from another person's, we can account for about 15% of that. All right, that was a lot of calculations, but now at least you have these videos as a reference you can always go back to if you need it.